I'm recording, guys, on these videos. I got to get my screen up there first. So I'll be posting this video into Canvas also. In the pages section, there's a folder for the class lectures. If you need to review something in the future, yeah, you can definitely do that. I wanted to give you a quick little warm-up problem. Talking about combinations Tuesday. And I wanted to do a little trickier example of kind of where combinations can come into a problem that doesn't feel like it's a combinations problem. So let me give you a warm-up problem to try. How many ways are there? So switching gears, we've just done the pigeonhole principle, but now we're going back into chapter 2 on counting strategies. So how many ways are there to seat 6 men and 8 women in a row? Okay, if no 2 men can sit next to each other. It's always those extra constraints that make these problems a little bit harder sometimes. So that's kind of what we're faced with here. How many ways are there to seat 6 men and 8 women in a row if no 2 men can sit next to each other? You know, if I didn't have that constraint at the end here about the men not sitting next to each other, what would be the answer if I just said how many ways are there to seat 6 men and 8 women in a row? What was that? I heard the word. 14 factorial, right? You would just have 14 chairs and there'd be no restrictions whatsoever. It's just as if there were 14 individual people. Put anybody you want in the first chair, anybody else in the second chair, somebody else in the third chair. It's 14 choices, 13 choices, 12 choices, 11 choices, all the way down, right? So that would be what it is. Okay. However, here we have this extra constraint that no 2 men are supposed to sit next to each other. So we have to think a little bit about how to set this up. Okay. So let me start working on the solution here. It's a little bit counterintuitive because I kind of hinted already that there's going to be some combinations here. And yet it seems like combinations are usually when order does not matter. And yet we are sitting these people in a row. There's literally 14 chairs. And it does feel like, if, Chris sits there and I sit there, that's different than if I sit there and Chris sits there, right? The order should matter, which seems like it should be permutations, right? Seems like it should be permutations. At least to me it does. Anyway, it's going to take a few tasks to seat these people into these chairs. And what I'm going to suggest that we do is, instead of imagining fixed chairs that we're starting to fill up right away, let's just get either the men or the women just arranged within themselves first. I'm going to do it with the women. Okay. So we can arrange 8 women in an ordered row. In how many ways could we do that? If we had 8 women and we were putting them into a row, how many ways would there be just to do that for the women? 8 factorial, right? 8 factorial ways. Okay, so there's 8 women, and maybe down here below my explanation, I'm just going to draw a little visual of this. Here are the 8 women. I don't know who they are or whatever, but let's imagine that we put them in a particular order. And what we have to do next is put the men, sprinkle the men in there. But I can't put all of the men over here because that would be too many men sitting next to each other, right? So I have to kind of use these women to kind of space out where the men are going, right? And where are the men going to be able to go? Well, to go to the left of the first woman, or between these two, or between these two, or these two, right? We can make these spaces around these 8 women, you see. So the places where a man can sit would be either here, 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 or here. However, you can't put 2 men in the same space, right? How many spaces do I have, by the way? 9 spaces, right? Okay, and I just got through saying you can't put 2 men in the same space because they'd be sitting next to each other. So what's another choice right now that we might want to make about the seating? We've already taken care of getting the women in order, but what about now we want to put the men in there? What kind of a choice do we need to make? Nikolai?
Let's choose one in the first slot.
So right here,
Yeah.
do I have to put a man here?
No.
Not necessarily, right? Because after all, there's 9 spaces there. I only have 6 men. So there's gonna be some spaces that don't get used. Does that give us a hint what we might want to do?
Then do 6 plus 8, which is 14, and 14 choose 1.
So
Or no, 13 choose 1.
I'm trying to wrap my head around where you're getting that from.
The 6 and 8 spot lives in 6 spot.
Okay,
But if
I
it's
see.
it would be but then it would
You know, of course, no worries. It's of course natural to just imagine, I'm gonna figure out who's sitting first, and then I'll figure out who's sitting second, and then I'll figure out who's sitting third. The problem is, in this kind of a scenario where we have this crazy constraint, right? What happens in chair number 2 depends on what you did in chair number 1 heavily. So if you put a man in chair number 1, all of a sudden now you have a different number of choices for what you can do in chair number 2 than if you started with a woman. If you started with a woman in the first chair, well, then anybody can sit next to her, right? But if you started with a man in the first chair, then the second chair can't be another man. So when we end up with cases that are kind of hard to manage in that sense, right? Where what happens in seat 2 or step 2 depends on what you did in step 1. You're either looking at a really long-winded, messy analysis that you have to do, or it's just not going to really work out one way or the other. So I'm tempted to look for an easier solution. I'll just put it that way. Yes, you have an idea?
choose 6.
Choose 6 seats for where the men are gonna go. Now you said 10 choose 6, but I'm going to edit that slightly. 1, 2, 3, 4, 5, 6, 7, 8, 9 spots, right? I'm gonna choose 6 of those 9 open holes to have a man sit, and that's actually where the combinations are coming, right? So we now choose 6 of the 9 spaces to put the men. And see, this is the weird part, guys, because actually it doesn't really matter what order you choose the spaces in. You could just say, well, I'm going to use this space, this one, this one, this one, and this one, right? You can circle like 6 of the spaces, but the order in which you selected those spaces actually doesn't matter. You're just going to pick them all out at once and now say, I'm putting men into those spaces. Okay, but that is where we get the 9 choose 6. There's a combination there. Michael?
Yeah, would 9 choose 3 also work?
Correct. Remember the 9 choose, or sorry, n choose k is the same as n choose n minus k. And so that would be just saying, well, I'm gonna choose the 3 spaces where no man is going to end up sitting. And that would also have worked, absolutely. Okay. And in fact, if you're calculating this without a calculator, it's probably easier to think of it as 9 choose 3. Because remember, you do the following factorial thing, and if I only have to go 3 steps down, right? Remember this thing I showed you on Tuesday? Factorial down 3 steps and up 3 steps. It's just a little less to work out than if I did the 9 choose 6. So yeah, so you could sort out what that is pretty easily, I think. And so that's the second task. Is there anything else we have to choose, or are we done here? Austin.
We have to order the men.
Right, once we have the 6 spaces that we're gonna have a man sit in, we have the 6 men that have to fill those 6 spaces, so that's another choice, and how many ways are there gonna be to do that? 6 factorial, right, so, we finally arrange the 6 men in these 6 spaces in 6 factorial ways. Exactly. So that's the third task. So you do see shades of order is important, right? When you see the factorial, right? The order that the women are in is important. The order that the men are in is important. But the getting the spaces where the men are going to sit, that's the little bit tricky part with the combinations, right? So then finally, by the multiplication principle, which was in the videos that you guys watched last week, by the MP, multiplication principle, the answer is, so it's going to be 8 factorial times 9 choose 3 times 6 factorial. Okay, and I actually prefer the answer to be written that way. Of course, you can get a calculator out and come up with a specific number here, but I actually like to see this at least because it shows me sort of the parts of the analysis that you had to do to get the answer. Okay. Questions on that? So I just wanted to show you that most of the time, I have to be honest, most of the time, these problems are some kind of a combination of combinations and permutations, right? It's not just a clear-cut permutation or a clear-cut combination. Did you have a question, Austin?
Yeah, I initially assumed one thing, which was the men and women are equal. Cause like, I was thinking like, if it was 6 like blue balls and 8 red balls,
Okay.
we could switch them around instead of same.
Oh, so that would be a different question, and I do this sometimes. So we have 8 identical twin women and 6 identical twin men. Right, so all the men look the same and all the women look the same as each other, and then how many ways are there to do this? Well, all that would do, it's a really interesting question. You would then not have to worry about ordering the women, and you wouldn't have to worry about ordering the men, and it would just be the part about getting the spacing that you'd have to account for. And so your answer would just be 9 choose 3 in that case. That makes some sense? Yeah, that's good variation. Uh-huh.
Because if you can put a man and women together, like, and then all you have to do last is the women and women together, and then just there's 7 different ways for the women and women to go, like in a different spot. But I think that's might be wrong because I don't account for when men go first.
Yeah, I was gonna say, if you're trying to glue one man to one woman, to kind of pair them up that way. Even though it's a little tricky for 2 reasons. One is, yeah, which one is on the left and which one is on the right. There's sort of 2 choices. And then the other part is, of course, you don't have the same number of each. I don't know, is it really fair to say that, yeah, so like if you decided to glue a woman and a man together, right, and then you glued another woman and man together, but you did it this way, then you're doing something that's kind of illegal there because the 2 men are standing next to each other. So I'm not gonna say that wouldn't work, that approach, but you'd have to be really careful and kind of make sure that there aren't any violations there. Yeah, so yeah, this is one of the things with combinatorics is you can get these tricky subtle points that you have to really be focused into to not overlook. Okay, well, so we talked about permutations of sets and combinations of sets. The permutations part, we did that in your video notes last week, and then on Tuesday I talked about combinations of sets. In both of those scenarios, I was not allowing for repeats. So this identical twins idea that we just brought up is essentially saying we're going to allow for the same object to occur multiple times, and you can't tell it apart from its identical copies, which of course reduces down the number of different things you can have. So this is a whole nother topic, right? It's a whole nother type of counting problem, and I wanted to start talking about that a little bit now. So the timing of Austin's idea was actually quite good. So let me come over here, and I'm going to just talk about this section. This is 2.4 in the book, and this is called permutations. So I'm going back to permutations again, but permutations of multisets. Permutations of multisets. A multiset is just a set where you can have multiple copies of the same object. So let's write this down a little bit, right? So this is going to be the scenario where repetition is allowed, but that order matters. A nice physical, on Tuesday when we were doing combinations of sets, I was talking about poker hands as being a prototypical example of a physical problem where you're doing combinations of sets. This type of situation, I like to use the license plates example, right? A license plate, obviously the order that the characters are in the license plate matters. But on a license plate, you can have the same characters, right? Repeated. So repetition is allowed. So this is kind of a good, just if you're trying to think of something familiar, you can think about license plates. Sometimes this is helpful, you know, to take some other problem that you're going to try to answer and ask yourself, well, is it like poker hands? Or is it like license plates? Or is it like photographs of people? That kind of thing. So use familiar analogies to relate the problems that you're thinking about with, and I think it can be helpful. So let's write down a definition here just to be very formal with covering the details of this. What is a multiset? So I'll just put that here. A multiset, by definition, right? A multiset is a set whose members, it is a set whose members need not be distinct. Okay, so again, normally if you have 6 men and 8 women, that would be a set of 14 people and every object is distinct in that set. But if we have identical twins, right, then suddenly we're talking about a multi-set in this context because there's members that are not distinct. So just a little notation that you'll see sometimes, and it's certainly in the book as well. I'll give it to you here. This is notation to help us talk about this. So if the object, let's say little a, occurs n times, so we have a particular object that comes up n times. Let's just write, so we will write that as n times a. That's just a notation. I don't want you to literally think of that as a mathematical expression because you're not literally multiplying the number n by a. A is just an object, right? So, but that's a notation. So just as an example of this notation, kind of help us understand what this is saying. If I had the set of A, comma, A, comma, A, comma, B, comma, B, comma, C, comma D, comma D, comma D, comma D, comma D. So I just write down a multi-set here. I see that the objects are not distinct necessarily. Right, this could be in shorthand. So this is A, and then B, B, and then there's a C, and then D, 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 D. See, we can just write that as 3.A, comma, 2.B, and then I have C, and then finally 5.D. So again, it's not really multiplying, it's just a notation here, okay? And then I should also make a quick remark, because sometimes we might have an infinite number of a particular object, like you have arbitrarily many. So an unlimited number. An unlimited number of, let's say, quote unquote, A, can be written as infinity dot A. So we can actually use the infinity symbol for that, if that helps a little bit. Did you ever hand up anybody?
Yeah, I was curious how you would say, like, would you say 3.A, 2.B, C, 5.A, would you say 5 times?
It doesn't matter. Yeah, it doesn't really matter. Yeah, you can just say 5 times D if you want. That's okay. Okay, so let's write down an example now. And then. Okay, let's write down a quick example. How many 7-letter license plates are there? So I was using license plates as like my familiar analogy that I can talk about here. So this is just another way of saying, I'm going to rephrase this question. Okay, and I'm just going to say how many, this would be a 7 permutation, right? Because it's going to have 7 spaces. How many 7 permutations of, well, you're never going to run out of A's or B's or C's, right? You can use, the alphabet goes forever. So the set that you're talking about would be a multi-set where you have as many A's as you want, unlimited number, as many B's as you want, as many C's as you want, and I'll go dot, 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 all the way up to infinity times Z, right? So this is just a rephrasing of the question using this notation that we just introduced, right? So, now, to be honest with you, even though we have infinitely many A's, of course, we're not going to use that. We're not going to use, even if this had said there's only 7 A's and 7 B's and 7 C's and so on, right? The answer would not change because you're only allowed to use an object up to 7 times. So anyhow, but in theory, there's no limit to how many of each of these letters we could have. Now, it would be another interesting question to say something like, you know, what if you could have at most 5 A's in your license plate, right? So that would then be a constraint, kind of like we had a constraint over here, that would reduce the number of license plates that would be legal. And so we can obviously tweak this problem, but let's just start with this one at least first. It's a little bit easier. We all know there's 26 letters, right, in this alphabet. And so I'm going to, you know, because order does matter, I don't mind at all writing down these slots. Be careful about drawing slots when order doesn't matter though. Because then you start putting things in order because it looks like something's to the left of something, to the left of something. Here that is totally legit because the order matters, right? When order matters, I don't mind having slots being drawn. And does somebody want to take a stab at this? Fernando.
You have 26 letters in the alphabet, right?
Yes.
So every slot you have 26 different choices to choose from.
Uh-huh.
You're gonna do that 7 times. So it's gonna be 26 and 7 times.
That's couldn't have said it better myself, right? You are making choices in each slot, and there's 26 of them for each slot. So I'm just going to write this. This is equal to 26 raised to the power of 7. And of course we could I like to give a little explanation. So as we're heading into the next homework assignment, keep that in mind. I don't just want to see chicken scratch with an answer. So like here you would say, you know, choose a letter for the first slot, something like that. Doesn't need to be anything like super fancy, but just at least tell me what you're doing. What does the 26 refer to, right? And then the second one would be, you know, choose a letter for the second slot. And you don't have to keep writing this. You can just say dot, dot, dot like that, and I'll get the idea. As long as I have the idea that you kind of know where these numbers are coming from, that would be totally fine. Okay, so, that is the right answer, and it sets us up to sort of state a pretty easy theorem here. I think I'll just go ahead and write the theorem down, pretty much without a proof. Okay, so this is theorem 2.4.1. I'm using the book's notation or the theorem numbers. And all that this says is that, let capital S be a multi-set with K different types of objects. With K different types of objects with infinite repetition. Because a lot of times that is the story. And again, I'll just point out that even if it's not infinite repetition, if it's enough repetition to cover as much as you're being asked to choose on your particular problem, such as here, 7-letter license plates, as long as you have 7 of every letter, you've got more than enough to have no constraints essentially, right? But here we'll just state with infinite repetition. So S is a multi-set, K different types of objects, each with infinite repetition. Then the number of R permutations of S, right, is, so in each slot, I have K choices for which type of object I'm going to use, right? And I have R slots in total that I need to fill because I'm talking about an R permutation. So this is simply K to the R. It is simply K to the R. That would be the answer. Okay. Clear enough? Okay so far? Yeah, a lot of times I'll be honest with you, like I don't memorize these theorems and try to memorize what goes for K, what goes for R. I tend to just, like Fernando just did, take the problem at face value and just kind of common sense my way through it, right? How many choices here, how many choices here, how many choices here, and so on, and that usually will get me where I'm trying to go. So, questions? Make pretty good sense? Okay, well, I was gonna do the Mississippi problem, but maybe I'll wait until next time to show that to you. We're kind of still working our way through chapter 2. I've only got like 2 minutes left, so I might stop 2 minutes early. Please memorialize that thought in your mind because this is unheard of. So if I go 2 minutes over sometime like 3 weeks from now, you'll all be very understanding, right? Okay, that's all I've got for you for today. Thank you so much. And I'll be downstairs if anybody wants to stop by. If you've got questions on tonight's homework, you can also come into Zoom 5:30 to 7, and then again from 8:30 to 10. I'm going to be around. I would be delighted to help out if I can do so. Have a great day, everybody. Drink a lot of water. Stay cool.
Thank you, Dr. Annan. I got all the notes and everything's good.
Great.
I'll see you in Zoom office hours.
See you next time. Yep.